Hello everybody, and nice to see you again. Welcome back to Ask Math Anything. And it's nice to know that, even though it's the summer, we don't necessarily have to stop thinking about math and asking questions. If you haven't been here before, I want to welcome you. We're gonna see what people are curious about. That's what we usually do in this live stream. And if you have any questions on the top of your mind about mathematics, feel free to ask. If you've been here before, we're going to say the same thing we say when we open every single time, which is that we usually try to cover topics that are useful and understandable to people who are studying algebra or geometry. And we'll try our best this time. I think that in the past session, I think we managed to nail that difficulty a bit better, and so we're going to keep trying to do that. Great. Well, I do see some people saying, not really. So we're gonna try to see what we can do. If it was too hard or too easy, we always like to hear from the audience, and that way we can make the best thing for you. Let's see, what kind of questions do we have today? Oh, these are interesting. Okay, I'm looking at these things. I see a bunch of different types of ones. I see one that's about something called geometric probability. Somebody has asked, it's Anonymous Panda has asked, if I have 3 points chosen randomly and independently on a circle, what's the probability that all 3 pairwise distances are less than the radius of the circle? I'll just say that this kind of a question is basically a question that's a little bit maybe too complicated for this group. Or is it? No, it's not. Let's do it. Okay, so let's do it. So I hope that this is not too hard. We'll see. Famous last words. This is a question by Anonymous Panda. And the Anonymous Panda question is, look, here's a circle. Looks sort of like a lump. I hope it's okay. But we got a circle here, all right? And Anonymous Panda says, hey, there's somebody out there. They're going to choose 3 random points on the circle. Like this one, and then this one, and then this one. And the question is, what's the chance that all of the distances happen to be less than the radius of the circle? Well, that's bad. This is bad. The reason that's bad is because that's longer than the radius of the circle. Looks like pi, you're saying. I guess it's like a big pie that I cut in this way. But the issue here is that somehow this is bad because that length is longer than the radius of the circle. So the question is, if you pick 3 points at random, I'm actually going to give some words now. Uniformly at random. Uniformly at random means that you pick one anywhere on the surface where everywhere is about the same likelihood, and then we just do it 3 times. Uniformly at random. And independently, that means that each decision doesn't affect the next one. The question was, what's the probability that I has an extra dot? What's the probability that all 3 distances are less than the radius? Okay? Now, if I look at this, the way I think about it is, it looks like I have to be really lucky to make all 3 distances less than the radius. In order to do that, I basically have to have all of the points mushed together on one part. Does that make sense to people? Because if you've got points like 1 there, 1 there, 1 there, oh no, that's bad. In fact, the only way I see to do this is if somehow all of the points are mushed on the same side over here. Does that make sense? Yeah, so the probability isn't going to be too high, right? That one was bad. Let's draw another circle. Wow, drawing 1 circle is hard. But drawing 2 circles that are about the same size is harder, because then you'll just look at it and you'll be like, well, that one was bigger than that one or something. But let's say this is close enough. Looks sort of like a lumpy potato. But so I've got this thing. And what's an example of good? An example of good is something like this. Here's this, this, and this, all close together, right? So in some sense, what's going on is that this longest side, this is the longest side, is less than the radius. Okay. Now, what's a good way to think about a question like this? Whenever I think of a question like this, I say, I have 3 points, and I'll put the 3 down. But circles, do you know what's the nice thing about a circle? Circles turn. So when I have a circle, I actually can say if I'm going to drop 3 points at random, just put the first one right on top. You can actually say when I drop 3 points uniformly at random on the circle, if I want to analyze this, I can assume that the first one dropped right on top, and then I just put the other 2 down anyhow. And the reason I can do this is because wherever the first one dropped, if the first one didn't drop on top, maybe it went there, poof. Well, then what you'd say is, yeah, sure, then 2 more are going to go down, but I could just turn the picture. Or like, who said what was top anyway? I could just go and take my paper and like go over to here. Oh, I'm not sure that makes as much sense because you're looking at a screen and I'm not able to make myself levitate and kind of turn 90 degrees. But you know what I mean? It's like it doesn't matter where that first one is. The whole thing is what we call rotationally symmetric. So let's just go and assume that the first dot is on top. That makes our life a lot easier. One moment. I also hear that my phone is making all kinds of little noises that I don't really want to bother you guys with. So if you hang on a second, I'll turn the notifications off. All right. So next thing. Now what am I doing? I'm drawing another circle. Oh, this looks like a pretty lumpy circle. All right. Yeah, it's okay. So I got this circle here, and I'm going to say that the first point dropped on top. That's my first point. Now, if that's my first point, I need to now know what's the chance that the other 2 points are such that they basically lie within the same 1/6 of a circle. What's so special about 1/6? Well, you see, here's 1/6. 1/6 is what you get if you take the center, and then you take, the radius, another radius, and another radius. Except that makes an equilateral triangle, so this is 60 degrees. Does that make sense? So the answer should be easy, right? The answer is just, look, I just need that the other 2 points both go there. So it's 1/6 chance that it's here, times 1/6 chance that it's here, so it's 1/36. How many people think this is right? I'm supposed to figure out the probability that all 3 points end up kind of close together. So why don't I just go and say, look, that's 1/6, right? See that 1/6? So now I'm just going to say, what's the chance the first one goes there? Boink. And what's the chance the second one goes somewhere in there? Boink. 1/6 times 1/6. What's wrong with that? Well, what's wrong with that is who decided that this was the green patch? Why is this? Yes, P14Y R0N3 says, whenever you ask that, the answer is no. You've watched too many of my live streams. You're right. So the thing is, like, you might have thought, like, look, that's 1/6 times 1/6. But the issue is, who gets to choose where this green thing is anyway? What if somebody else says, I prefer the green thing that goes over here? And look at that. You can pick this one and this one. These 2 points. That also works. And they're not even in here. So you can't do that. So if I can't do that, well, then what can I do? Here's something else I can do. 60 degrees. Another 60 degrees. That didn't look like 60 degrees. This is sort of more like 60 degrees. What if I say here, let's do this instead. You first pick 1 point, which is somewhere in this 1/3. And, we'll pick 1 point. Maybe that 1 point is here. Boom. And once you've picked that 1 point, now you know which piece it has to be in. So maybe the answer is now 1/3 times 1/6. Who likes that answer? Well, I think you guys have watched too many of my lessons. You know that answer can't be right either, or else I wouldn't have asked the question, right? So it's not 1/3 times the 1/6 that it happens to be in. Why? Why not? Because watch, if this was the 1/3 and it went here, well, here's another way you could make it work. You could make the 3rd point just be like right over there. And if it's right over there, the distance between it and the blue point is still not more than 1/6 of the circle. So you can't do that either. V4913 says this is actually a very hard question. Well, here's how we can think of it. The way you think of it is you say, let's draw a picture. Let's draw a different picture, okay? I'm going to pick 2 points. One of the points is going to be blue. Oh, I need to think of a direction. You guys probably like clocks, so we'll go clockwise. I think of a direction. That's the direction clockwise. What's the direction for? Well, I'll pick 2 points. One point is blue. Oh, that's a terrible place to choose a blue point, but that's okay. I'm just going to say that's one blue point. And then here the other point is green. Now, supposing I picked that, I'll draw a different picture. Circles are hard to draw, but squares are easy. Famous last words. That's not a very good square, but it will serve. So that's a square, okay? So we got a square now. And what I'm going to think of this square is that the blue is on this axis, and the green is on this axis. What do I mean by axis? Well, where's the blue? The blue is not quite a quarter of the way along. I think of it as x and y in some sense. What fraction of the way around does this look like to you? Maybe to me it looks sort of like 20%. You know, like 25% would be all the way. To me it looks sort of like 20%, okay? And where is this guy? This guy, if this was a clock, where is it? It looks sort of like, it's like 5/8 or something. So let's just try to make those up. Let's consider this is at 20%. And I guess I need to actually think of a percent for this one. Let's just call it 70%, okay? It's not necessary. These aren't actually exactly right. I'm just going to give you some idea. And the reason I want to use some numbers is just so that I can draw it over here. So let's pretend this was 70%. Oh, that doesn't look like 70%. That bothers me. Because 75% is over there. So that's more like 65%. Or let's call it 2/3. 2/3, 2/3. I think somebody here might already have written that. So this is 2/3. And if we have fractions, we don't want to write percents at the same time. Let's call that 1/5. Okay, now here's what I'm going to do. I'm going to say that if the blue one was there and the green one was there, we'll draw one dot inside this square. And I'll draw the one dot right here. That's in the wrong place. I'm staring at this because I want to put it in the right place. Now, can anyone tell me how I chose where to put that? Where did I put that and why? What does that point mean? And don't worry, this is actually not too hard. We're actually about to learn something pretty powerful, but if you just pay some close attention, you'll be able to understand everything. Okay? It's not actually like calculus. It's not hard. It's not hard. So what's going on is I'm saying, remember, the first point is the purple one. It just went pop, and then it happened to be on top, or else we turned it. And I see a lot of people are saying where we're putting this is we're putting it at the coordinate where the x coordinate is 1/5, right? That's where it is on the x coordinate. And where it is on the y coordinate is 2/3. How can I write that? Like this. Does that make sense? So you see, here's what you can think of. If I want to know where the next 2 points go, I have a totally different way to do it. You just look at this square and you throw darts at it like a dartboard. You know, suppose that what I just did is I threw a dart and bam, I got here. If I got there, what would that mean? If I got there, what that would mean, oh yes, P14, Y, R0, N3, that's assuming it's a unit square. It is a unit square. That's very important. So what I just drew here is I drew a unit square. That's why that's 1/5. That's why that's 2/3. So I have this unit square, and you're saying, yes, dartboards are circular. So in fact, this is not a realistic dartboard, because in dartboards you can also go, bam, and you missed. You know what I mean? This is like a dartboard where you always hit the dartboard. So I'm saying this dartboard, you can hit anywhere on it, and you hit anywhere with equal chance. But if the place that you landed is right there, what that means is, that means that you put the blue dot, let's now clean this up. Where would the blue dot be? Let's work on this. Right? If I had dropped the dot there, then my blue dot is almost all the way. Almost all the way. Where is it? About that much short. What is that? Maybe it's around here. I'm making it up. All right? I'm saying that if I'm there, then the blue dot's almost over there, almost all the way around. And how about the green dot? Well, the green dot's at about 1/3. It looks like it's just short of a third. All right? So then the green dot is somewhere around here. Does it make sense to everyone that if I choose a random point on this square dartboard, that one random point tells me 2 points position on this circle? That's the most important part. And once we have that, we can solve the whole problem. Does this make sense? Yes. Okay. So now, let's now solve the problem. So we now are going to say, what were we trying to do anyway? We were trying to know whether or not I can find 2 points where the 2 points are both like such that the farthest distance between them is like a sixth of the circle. Well, in that case, let's go to this dartboard and let's go and try to indicate what are the points that are good. Let's clear this off now. What are some points in the dartboard that are good? Good for, something that gets me 2. Actually, every point here is good. Actually, that's not true at all. No, I take that back. In order for the points to be good, first of all, the points have to be not too far away from this pink thing. In order for the point to be not too far away from the pink thing, either the blue and the green thing have to be like really close to 0 or really close to 1. Does that make sense? So in particular, I couldn't choose half-half. If this was half-half, I would have said one point went there and the other point went there, and they're both not happy because they're too far away from here, right? So in order for this to work, my blue point, first of all, let's just think even the blue point. The blue point is only allowed to drop within 1/6 after and 1/6 before. So the blue has to be somewhere here. Are those sixths? That looks a bit big for a sixth. So far, all I know is that the points that I pick for blue has to be somewhere in there or there. Does that make sense? I haven't yet thought about green, but I mean that there's no way I could use a dart that ended up anywhere else, because if the dart ended up anywhere else, the blue is already dead. Right? If you end anywhere else, the blue is like, sorry, I'm already too far from the pink point. I'm not happy. It's over. Okay? So that means that from the blue, you've got to be in here or in there. Oh, but the green's also going to say the same thing. If the green ends up being somewhere in the middle, like a green value being somewhere in the middle, green's going to say, that's no good. I'm too far away from the pink. See, people are asking, what's the question? The question is just, if I choose 3 random points on a circle, what's the chance that the farthest apart any points are is the radius? And we've already reduced it down to this problem of saying, let's suppose that we have 1 point on top of the circle. What's the chance that if I put 2 points on the circle, those 2 points end up being very close together? Okay? So now, I now know the blue is saying I'm not allowed to go inside this zone, so I have to be in one of those squares. But the green's going to say the same thing. So once you factor the green and the blue together, the green and the blue together are going to say it has to be inside here or here. Up here means that you have huge green and small blue. Huge green and small blue would mean green is up here, very close to the end. Blue is over here, very close to the beginning. So now I know it's got to be in here. Right? Because I say that wherever the green is, the green has to be within 1/6 of the beginning or within 1/6 of the end. So now I have 4 pieces and each piece is 1/6. I need to let someone in. 1 second, please. There's somebody else who needs to come into this office. I'll be back in about 30 seconds. Hang on. Hello again. Hopefully I'm back. Okay, let's see. So now where are we? So now we know that we have, oh, who is it? Well, we have some people here who help to work on the math that's behind Novid. It's a fellow mathematician, exactly. So now, well, also a computer scientist. But let's go back here, right? So now I know that I want to go and find what's the area of these four things, but I'm not done yet. You see, I now know the answer is less than or equal to a sixth times a sixth times 4. And that happens to be 4 over 36, which is 1/9. But that's not the right answer either. The reason that's not the right answer is because there are some points in this diagram which are also not okay. And what does that mean? You see, right here, what I've drawn in this diagram is I've taken into account whether the blue is close to the pink or whether the green is close to the pink. This picture is all the points where the blue is close enough to the pink and the green is close enough to the pink. But now how do I also take into account that the blue and the green need to be close to each other? Well, if I want the blue and the green to be close to each other, then what I need to start to think about is, all right, so if I had a green which was like over here, or what's the easier way to think of it? I'm actually myself trying to think right now. What does it mean to say that the blue and the green are close together? To have the blue and the green close together, if the blue and the green were the same, oh, here's the easiest way to think of it. I think if I look at this, this is where blue is big and green is small. That's actually okay to an extent. Yes, I'm thinking, okay, right. So now the way I'm going to think about this is I'll say, in order for the blue and the green to be close together, here's one extreme where blue equals green. Blue and green are completely equal for all of the points on the dartboard that are on this line. That would be if blue equals green. But now, you know, that's like pretty lucky, and there are almost no points there. And for blue to equal green, that is actually, you know, that you don't need that. You just need that blue and green are close together. So in order for blue and green to be close together, where close together means close together by up to 1/6, what happens is that you can make this thicker. So in fact, all of these points here are where blue and green are close together. When I drew that thing across, I'm now going to erase this here, and I'm going to say that everything that's inside here has blue and green close together. Are people okay with that? It's like you basically said blue equals green is this thing that just goes straight across the diagonal, because that is all the points where the blue amount and the green amount are the same. But now if I want to say, well, blue could be close to green, then you make it a little bit bigger, a little bit fatter. And how much fatter? Well, it just has to be fat enough so that the height of it, like the height of it happens to be the 1/6. And the way to think of this is that somehow if I had a point over here, that point would be that the blue is at 1/6 and the green is at 0. If the blue is at 1/6, blue is here and green is up there, and it's okay. They are 1/6 apart. Okay. So it looks like then the answer is, I just have to say, I need to know what's the area of the yellow stuff, which is also in the pink stuff, right? Yellow means blue and green were close enough to pink, and then the pink thing means blue and green were close enough to each other. But there's one problem. That's the wrong answer too. So that would give us the answer of 1 over 36 plus 1 over 36 of 1 over 18. The reason that's the wrong answer too is because actually the line, the thing where the blue and green are close together, it's sort of like this game. I'm not sure if you've ever played it. It's called Asteroids. The game of Asteroids is where if a spaceship is going up here, you know what happens? Then it somehow goes boink, and it comes out of here, and it keeps going. You know what I mean? And if the asteroids ship goes over here, then boink, it comes over here and keeps going. Does that make sense? So that's the game of Asteroids. That's the same thing here. So in fact, the part that's considered close together, blue and green close together, when it goes to this, it teleports over to there. Zoop. And I actually want to only keep this half. Okay? So what I'm saying is that this part where blue and green are close together is this entire stripe, but also the points up in that top triangle have the blue and green close together. In that top triangle, what happens is that your blue happens to be tiny, but your green happens to be huge. And the more tiny your blue is, the more lax green can be. Like if blue is really tiny, meaning blue is really close to here, green can be a little bit more that way. Okay? So that's why I'm counting this top triangle also. What I'm trying to talk through here is what are the points on this dartboard for which the green and the blue, for those points, are green and blue close enough together, and also green close enough to the top, and also blue close enough to the top. So that half is important. The other half is actually bad. In the other half, the blue and green are too far apart. That would be sort of like saying, in the other half, it's sort of like saying, hey, I made the green go over here and I made the blue go over here. And now the green and blue, they're close enough to the top, but they're too far from each other. So now I do it for the other side. When I do it for the other side, it's the same asteroids game. It's coming around to here, boink, goes over there. And then I want to also count this bit. So that's where I'm going to get my answer. My answer is going to be, it will be the fraction of the area that is yellow divided by the fraction of, divided by the whole square. Actually, that's what fraction means. It's just the fraction of the area that is yellow. Because the yellow parts that are from here and from there, those are blue and green very close to this dot, but at the same time, blue and green are also close enough to each other. I'm just double checking to make sure that this makes sense to me. And yeah, that's good. So basically inside this part, inside this square is just called blue and green are both over there. This square is called blue and green are both over there. And then this triangle and this triangle are the cases where kind of like there's some blue here and there's some green there. Now let's just add everything up. I have 3 of these squares because I have 2 full ones and 2 half ones. So now I can finally finish. The area fraction is equal to 3 of the squares, 3 whole squares, and each square is 1/6 times 1/6. And so that is equal to 1/12. So that's my answer to this question. I hope it's right. I don't actually know what is the answer to this question, but hopefully some of you who might be following, I hope that this makes sense to you. The basic thing here is if you ever want to do a problem where it's like I choose 2 points or something, then you can actually go and think of it like a dartboard. I did see a bunch of people say they got 1/8. So I'm not entirely sure how you argued the 1/8. There's a possibility that when you argued the 1/8, you might have double counted something. So that might be the case. I'm actually not sure. If the moderators have figured out the answer to this question and it is 1/8, that would be great if you can let me know. But otherwise, what I would say is, it looks to me like what's going on is that if you draw this dartboard, which is how you should think about this thing, then the fraction of the dartboard that really has the green and blue close enough to each other and close enough to the top is only 1/12. So, okay. It's a very, actually, it does look like it was a pretty hard question conceptually in the end, but I tried to explain it slowly because I know it took half the live stream. I wanted to kind of explain it step by step so that the next time if you ever run across a question like this yourself, you can also try to draw a dartboard and just like stare at the dartboard to think, where are the points that correspond to what I actually want to count? All right, let's go to another question. All right, so let's go to something that's a bit lighter. We just did something pretty heavy, and in fact, this is a really useful concept. But somebody asked a puzzle. A puzzle is, this is from Daniel. Daniel says, I am an odd number. Take away a letter, and I become even. What number am I? An odd number. You take away a letter, and you become even. Okay, oh, you guys are so good. You guys are so good. Okay, you're brilliant. I was thinking about all these other actual numbers. I agree with the answer that's coming across here. It's 7. Okay. Whoa, that was nice. More questions. This is great. When I ask these questions and I don't know the answer, you guys can all answer for me. Love it. Oh, that's great. Somebody said that their name is Stephen, and so they know that that this happens to have this nice property. Hmm. What? Moonwatcher123, you have another puzzle. You're saying, I'm going to write down your words because they're very important. I add 5 to 9 to get to 2. Oh, I like this. I like this. This is correct. How do you do this? Yes. This is good. I like this one. Oh, you guys are so fast. Curious person says mod 12, a clock, timed like the afternoon. Yes, I think it's because we were just thinking about this, like this circle thing. So it is like a clock. It's just because this is on the clock. On a clock. Nice question. And we also saw that somebody answered that's like mod 12, right? Oh, come on, curious person. I already mentioned you, didn't I? I said some comment that you had. Okay. More questions. What is this? So somebody has asked me a Bob the Cat question with bananas and monkeys. Bob the Cat eats bananas every day, but he has to get past the monkey. He has a half chance of succeeding. But what is the chance Bob the Cat doesn't eat bananas for a leap year? I think I'm not entirely sure. Oh, I think what you're sort of saying is that if there's a half chance of succeeding every time, and you do this for 366 times, what's the chance that you succeed? It's really small. It's 1/2 times 1/2 times 1/2 times 1/2, because every single day is another 1/2 chance. And eventually you get 1/2 to the power 366, which is like kind of small. So yeah, exactly. Skylar Schreier is right. 1/2 to the 366 is very, very unlikely. Okay, more questions. Okay. Here's a question which is not quite about a math problem and also not quite about a riddle. This is by Evie Shen and asks, could you add this question? Is there any math in games like Minecraft? Yes, there's a lot of math in games like Minecraft. Actually, I think in Minecraft, the levels are also like randomly generated, right? So whenever people are coming up with the ideas of what will the world look like, there's a lot of math in thinking of what would be a good way to distribute all of these like resources in the space, right? And also, I think that there's probably a lot of math in the design of what you're actually trying to build. Actually, if you think about math and you think about ancient civilizations, one of the things that they really need, they needed math for two big things, if you think of ancient civilizations. And that has some relevance to Minecraft. The one biggest thing that ancient civilizations needed math for was so that they could solve math contest problems. No, that's actually not true. Math is not for solving math contest problems. It was for something much more fundamental. The math was so that they could survive. It was so that they could know when to plant the crops, right? I mean, if you think about it, at some point humans started to plant crops and grow crops. Well, if you're going to grow crops, it's a really good plan because then you're sure to have food later. You know what I mean? Like survival is not fun. Skylar, you're right. Like if the way that you survive is called every day go to the jungle and attempt to wrestle with alligators and eat them, this doesn't work very well. I'm not really sure that anyone does that in real life anyway. That alligators are probably the wrong example. But like you go into the jungle and you wrestle with something else that probably you can eat that can't eat you. But something like that, right? But like that's very, very risky. It's hard to go and hunt and gather. So at some point, civilization decided that they could just, plant crops. And that's great because you're just guaranteed to have food to eat. That's amazing. That's actually amazing. Now, there's only one catch. If you want to plant the crops, when do you plant the crops? Suppose you have this brilliant idea and you decide to do all your planting at the beginning of August. Do you know what will happen to your little city? Let's pretend that you live in, I don't know, somewhere in the northern United States of America, like New York, and you decide that you're going to plant all your crops on August 1st. What is going to happen? Yes, it will die, because what will happen is that it will get cold, and then suddenly your crops don't grow. And that was bad, right? Similarly, it's a really bad idea to plant your crops on that first day of February when suddenly the sun came out and like, wow, it was 60 degrees in February. Maybe I should plant all my crops right now. But, oh no, then that would also possibly not work well because you just had a freak day that was warm. You plant all the crops and then they all die also, right? So you have to actually plan this very carefully. And the ancient mathematicians were very interested in astronomy so that they could try to figure out, you should plant here and you should harvest there. And at that point, you can survive as a civilization. That was one big use of math. Now this is, Po-Shen Loh on farming, exactly. But this is not so useful for Minecraft. The other piece that people needed math for was construction. So you see, the thing about planting and growing crops is it's one of these things where you start and then things happen for a long while, and you hope that when you started, you made the right choices. Because if you made the choices and start going for a while, you're kind of locked into them. You know what I mean? Now, if you're going to go and build a huge building, it's the same thing. You can't go and say, I'm going to build a house like this. It's the same way I build a Lego house. I just kind of put stuff in whenever I feel like it. And it's like, yeah, I think I'm just going to add this like bunch of pipes over there. Oh, actually, ancient civilizations might not have had the pipes. But it's like, I'm just going to go and add a bunch of things here and then add a bunch of things there. This is a great way to make your house collapse. All right, so actually for architecture, people had to use a lot of math to go and think about how you would build this Egyptian pyramid. And so now the math in Minecraft, if you happen to be interested in building stuff, I would recommend one thing, which is kind of plan it out first. And when you plan anything out, you'll probably find that you're using math to do so. All right, more questions. Ask history everything, apparently, is what somebody is saying now. I mean, I'm not a historian. I'm not anything. I'm just a mathematician. But you can see how if you're a mathematician, you can kind of use that to think about things and maybe come up with an explanation. By now, we might have more questions. Oh, a puzzle. Have we done this puzzle before? If we have, then you guys will tell me the answer right away. Moonwatcher 1, 2, 3. Arrange 4 nines to get 100. Wait, that's not that bad. Yeah. I'm okay with that too. 99 plus 9 over 9. I like that. So I would say 99 plus 9 over 9. I'm not sure if that was the answer Moonwatcher was looking for, but I think that seems quite reasonable. All right. Well, yes, that's assuming that we can smush numbers. You're right. But what else could we do anyway? I'm not really sure we have any more space to do anything else with this problem, so I'm guessing that's what it is. Okay, but thanks for sharing that. I see that Unknown Monkey is saying that we should do AMAs where we only focus on one topic, like geometry or number theory. We are only focusing on one topic. The topic is called math. Well, okay, let me be more specific. We are also trying to focus on things that are understandable to people who are studying algebra or geometry. I've chosen not to go to talk about number theory because I'm trying to bring more people into this interesting world, and so we're going to start from something which is more basic. Okay, more questions. P14Y is asking to find 3 positive rational numbers, A, B, C, so that A plus B plus C equals A times B times C equals 7. You want 3 positive rational numbers. That's what makes this hard. Something else that makes it hard is that my pen doesn't seem to write right now. Let me just quickly restart my drawing program and we'll be right back. Okay, here we go. So now we want to find 3 rational numbers, right? We want to find 3 rational numbers so that x plus y plus z equals 7, and also x times y times z equals 7. But the trick here is you want 3 rational numbers. Well, rational definitely makes it a lot harder. If I just could find any 3 numbers, that would be a lot easier. Oh, and they have to be positive. Thank you very much. So let's add that they have to be positive. Okay. Well, the first thing I'll say is that if I see x times y times z equals 7, that's not going to be fun. And the reason that's not going to be fun is because, well, I have to have things that, divide into 7. So that's not good. Yeah, whole numbers are rational. That would be nice, but I'm not going to find any whole numbers here, right? So, I mean, if I do it with whole numbers, I'll need to have 3 factors of 7, like 7, 1, and 1, and that doesn't work. So I don't actually know how to do this yet. I hope it's not too hard. Famous last words. I'm going to go and do what I would do for this problem, which is to say, let's go and figure out everything in terms of a third number. Meaning, if I had 2 equations and 2 unknowns, I can solve that. All right? So let me just say, let's pretend that z is like something else. I want everything in terms of z. So I'll show you how I would think of this. This is actually an interesting question. So if z was just something, I'll write x plus y equals 7 over z. I strike through the z so you can tell it's not a 2. And my other equation is xy is equal to, no it's not, something's wrong, I can't do that, 7 minus z. And the xy is 7 over z. Okay? So now, what I'm going to do is I'm going to say, let me try to solve for x and y. If I have these 2 equations, I could figure out what x and y are, right? I've got 2 equations, 2 unknowns, and I'll figure them out in terms of z. Why I'm doing this is because this is going to give me a quadratic equation in x and y. Quadratic equations give me square roots. And I'll see like what about these quadratic equations I need to be true in order for the square roots to be like rational numbers. And that will tell me conditions on z. Okay? I don't want a hint. No, I have an idea. I see this. I think we can do something here. If I see x plus y and xy, here's what I usually do to solve this. I would first go and say x plus y, let's square the x plus y. That is x plus y whole thing squared, and that equals 7 minus z whole thing squared. I'll simplify later if I need to. I first want to know what I should simplify. Well, that's x plus y whole thing squared. And if I look at that, I can definitely square root that, right? And I already see x plus y is there, it's fine. The next thing is I know I can get an x minus y whole thing squared. The way I'd get x minus y whole thing squared is, you see, if I expanded this thing out, this would be x squared plus 2xy plus y squared. That's x plus y whole thing squared, and that happens to be some nonsense. I'll simplify later if I have to. Now, why is that important? The reason that's important is because I already know what xy is. So I could figure out what x squared minus 2xy plus y squared is by just subtracting 4 of those things. 7 minus z squared minus 28 over z. Are people still with me here? So what I've just found out is that, this thing here with the minus, that one makes sense. I just take that guy minus 4 of those. Okay? Oh, you can't square both sides. Are you sure, Carbon News? I'm saying that I'm trying to find the solutions to this thing. Okay? This problem is possibly pretty hard. We're going to find out real soon. But what I have to do here is that, I'm trying to find out what are all the x's and y's that might work. And the way my logic is working is I'm saying, suppose there was x, y, and z that worked. Here are some equations that are true. I'm going to mess with these equations and do stuff and see what I can conclude about x, y, and z. So now, if I squared both sides and then I subtracted 4 of that, then I would get this. And that's good because that's x minus y squared. That's equal to just this 7 minus z squared, 7 minus z whole thing squared, minus 28 over z. And here's where I see, so I could get x minus y by just taking the square root of that. So you see, if I could take the square root of that and get a rational number, then I would get equations x minus y equals rational number, and x plus y equals rational number. if I have those equations, if I get to two equations which are x minus y equals some rational number, okay, it doesn't really matter what it is, between this equation and this equation, you can solve for x and you can solve for y. And when you solve for x and y, you basically just add rational numbers together. So now I have reduced the whole problem to saying, I just need to know, is there any rational number z that makes this thing a perfect square? So I had three variables before. Now I have only one variable. Did that make sense? Because before I was saying, I've got an x and a y and a z. I don't know what to do with all these. But I'll say, suppose that z got locked down first. If z got locked down first, let's solve for the x and the y. And as we're solving for the x and the y, we find out that there's a step that I need to take a square root. And once I'm done with the square root, then whatever I have left is just a plain old x minus y. And a plain old x minus y equals some number, together with a plain old x plus y equals some number, is something I can solve. So now I have a question. Yes, actually you're right. P14, you're right. Don't you have to take the positive and the negative square root? You do have to take both into account. But what I'm doing right now is I'm just trying to find you the x, y, and z that work. And if I find the x, y, and z, I'm just going to plug them in here and see if they work. And if they work, I'm done. And in reality, I would need to worry about the plus or the minus. I might have two options. But right now, I just need to even know, is there any z that, any rational z that if I throw in here gives me something I can take a square root of? That's all I have left. Okay, so is there rational z so that this 7 minus z squared minus 28 over z is a perfect square? Whoa, that looks hard. So this looks legitimately hard. But I have an idea. Okay, let's use a difference of squares. Okay, so the way I would figure this out is, some people told me z equals 28 works. Maybe, I'm not sure. Are you sure z equals 28 works? I'm not sure z equals 28 will work very well, because if I put z equals 28 here, I get like 21 squared minus 1, which is not going to work. Oh, maybe it does. I actually don't know what is. No, it can't work. 21 whole things squared and then minus a 1 wouldn't be able to work, right? Because if I put z equals 28 here, this whole thing goes and just becomes a 1. So that wouldn't work. So I'm now double checking. Some people seem to think that it works, but I'm not entirely sure. I don't want to hit now. No, not yet. The way I want to solve this is I want to say, if I want this to be a perfect square, I'm going to give the perfect square a name. Let's call it a squared. So now I need to know, is there a way so that 7 minus z whole thing squared minus 28 over z, could this be equal to a squared? Find z and a rational. The reason I want to do this is because this matches a difference of squares. And I also see something here I might want to factor. So if I do a difference of squares, put that over on the other side, I get 7 minus z plus a. 7 minus z minus a is equal to 28 over z. Aha. So now that's interesting. Wait a second. Is this doable? Ooh. See, as I'm looking at this, I'm basically saying, if I want to do this, I need to have that the z has to be something which, I could put into here. I want to factor something. I want to factor something out. I want to basically factor the 28. So if I wanted to do this, I guess I would have to factor out the 28 to put, no, this doesn't look that nice. So I actually don't see a nice way to do this. Because I don't really like the fractions. If z was 1, is that possible? That's not clear either. Yeah, z equals 1 is something that I find tantalizing. I wonder if I can do that with z equals 1. That would be really nice. So if z was 1 though, well 7 minus 1 is 6. 6 squared is 36. 36 minus 28 is a hard problem. That's 8. So that wouldn't work. So that wouldn't work either. So if I used z equals to 1, then I would get 36 minus 28, which is 8, which is not a perfect square. So that doesn't work either. Wow, so this one's actually not that good. Right, so this one maybe is a little bit too difficult for this group. The reason I'm saying that is because I was hoping it would be something nice that would happen out at the end. But yeah, this one might be a little bit too difficult for this group. I'm just thinking if we can do something here. Because if we just guess and check, that's not effective either. But what we're going to do here is like we'd have to split apart this thing. I'll just tell you what I would probably do. I'll try to split this apart into something like 2 times 14 over z, or like 1 over z times 28 or something. And maybe this would work. But let's do this. Let's not dwell further on this because we didn't want to go too deep into something that would be too far beyond algebra or geometry. So let's not continue on this one just because of the fact that it looks like here we're going to have some difficulty. Okay. More questions. We're gonna move on to another question just so that we can try to cover as many things understandable to people as possible. I know that you can have solutions, and I see that you have solutions you can give. Don't give the solutions because it's more interesting to go and play with this. But the way you'd have to think about it is this number theory that's going on right here. Okay. Oh. Huh. What is this? So this is a puzzle from Daniel. Daniel says, what 3 numbers, none of which is 0, give the same result whether they're added or multiplied? That sounds interesting. What 3 numbers, none of which are 0, give the same result whether added or multiplied? Well, I would just say that whatever were the answers to that previous problem would be just fine. The previous problem would give me 3 numbers that add to 7 and multiply to 7. But I see that you guys have another answer. 1, 2, 3. That's pretty good. And yeah, I see that people are also saying this other thing with the 7. What you're seeing is there's actually infinitely many solutions. There are lots and lots of different ways to do this. So, the 1, 2, 3 happens to be a solution, and whatever else was the solution to the previous problem also happens to work. Okay, more questions. And I wonder if we could, I'm not thinking, that's nice. 1, 2, 3 works. It would be really neat if I could use the 1, 2, 3 to solve the previous problem. But I don't really see a way I can easily make a 7 appear. So we won't continue. Okay, more questions. Michael Xiang asks, at what points on Earth can you travel in a perfectly straight line and go due east at the same time? Ah, okay, that seems like an interesting question. Going due east at the same time while traveling in a straight line. That sounds easy. I have the Earth. Oh wait, I shouldn't have drawn that yet. The Earth! Everyone knows the Earth is flat, okay? This is the Earth. Nice flat Earth. So we've got this Earth, okay? So what we have is that at what points can you go due east? And it happens to be a straight line. Well, you see, now this is a little bit tricky because it's like, come on, everywhere. All you do is you just go and start from anywhere and go in a straight line east. The issue is that those aren't straight because the Earth is a smushed sphere. Like if you imagine what actually happens on the Earth, if you ever fly around, it's been a while since we did that, I guess. But if you fly around on the Earth and you fly from here to there, you may have noticed that the plane does this. And the reason the plane does this is because somehow if I have a sphere, the shortest path from one point to the other is sometimes over the North Pole, right? And I mean, as one example, if I ever fly from New York to Beijing, it actually usually flies over the North Pole because that's actually the shortest path. So actually on that map in the airplane, what it looks like is it looks like you're doing this, and then suddenly it goes zoom and you get there. because the map actually shows like where you are. And as it's showing where you are, you kind of very slowly go north until you get up here. And then like really, really fast, you kind of teleport over there. And then you slowly go back down. And the reason is because obviously when you get all the way up to the top, the distance between that point and that point is actually very close. For example, if you got all the way to the top at this North Pole, in like one step, you'd be able to take one giant leap for humankind and walk over to there. You know what I mean? It's actually pretty neat. If you just stood over here and you were really at the North Pole, you take one step and you're over there. Okay? Now, this question is asking, when is going due east going in a straight line? At that point, the answer is going to be that it has to be on the equator itself, because that's the only way that you could go straight. Although somehow you could also say, is it really straight if it's still on the surface of the Earth? Maybe you never go in a straight line. Maybe you always kind of go along some kind of a curve. But the only time the curve really happens to be that straight thing is actually when it's on this equator. All right, more questions. We have about 2 minutes left. So usually whenever I have 2 minutes left, I try to choose something which is like a nice general answer, a nice general question to answer. Oh, neat. I see people are saying, please collaborate with Richard Russick or AMC Australia. That would be a great idea. Actually, that could be a lot of fun. Good idea. Right. I see somebody is asking, David Sia asked about, please explain statistics and why it is so useful to us. I'll tell you why statistics is useful. I was doing a scientific experiment yesterday. Some of you know that I'm working on this app called Novid, which is trying to be able to protect you from getting COVID-19. And one of the things we did is we went and we made it possible for smartphones to measure distance using ultrasound. And now the issue is we kind of, we knew we could do this, but nobody knew how accurate it was. That's what statistics is for. So in fact, what I did yesterday with some help is that I went and we measured about almost 600 different measurements of phone here, phone there, look at the distance, see how far apart they are. And what statistics helps you to do is it helps you to not just get like a number, because it's actually very interesting. As I was writing up the laboratory report, it dawned on me, that's why it's so useful to be able to have methods to summarize information. Because if all I have is, I did all these measurements, and look, this distance is the real distance, and here's what it measured. And this is the real one, and here's what it measured. How would you even figure out, whether you're doing well or not? But the statistics can help you to summarize. Even notions like mean and standard deviation let you very quickly understand that, oh yes, all these things that I measured, their mistakes that they're making are off by about how much. And let me just close with just one example. There was something we were doing yesterday when we were measuring, and we got a bunch of measurements, and we wanted to have a sense of how close together they were. Because, for example, if I measure 3 times, and the 3 numbers I get are 160, 165, and 164, those kind of sound close together. Sometimes we measure, and we get like 90, 250, and 127. Those sound far apart. Is there any way to try to say how close together they are? Well, one way is to calculate what's called the range, is to say take the biggest one minus the smallest one. You could do that. But that's actually not exactly what you want, because sometimes it matters what the number is in the middle. You actually want maybe you want a different notion of the answer if it was like 200, 200, and 100 versus 200, 150, and 100. So that's an example. Statistics is good for letting you try to understand how to summarize that situation. And based on the statistics I'm getting, which is called the feedback from the crowd, it seems like we are over time. So in that case, unfortunately, we're going to have to close out today's live stream, but I'll see you tomorrow. Take care.